Okay, so let's start putting everything together so that we can put the fundamental question of the feasibility of learning and can we really accomplish the task that we started at, the two-step learning process in which we wanted E out to be as close to E in as possible, right? So essentially, we want to answer two questions regarding that. The first one is, can we get a polynomial bound on the growth function even for infinite h? And I think we already proved that part. And the answer to that question is yes. And we do have a bound on the growth function even for infinite h. Okay, so that has been answered. And then we've also analyzed the two different types of hypotheses that we can encounter. The next thing that we need to answer is that can we replace the total number of hypotheses sets, the cardinality of the number of hypotheses sets, with m sub h of n in the generalization bound? That's the key question that we really need to answer, because now we've come up with a polynomial value for this thing. But if you remember the actual generalization bound or the Hofting's bound, in the error bar, we still have the h, the cardinality of h in there. The answer is yes, we can replace that. Why? Because we are interested in the effective number of hypotheses, right? We are not interested anymore in all of the possible hypotheses, because we figured that they aren't as useful as the effective number of hypotheses. So we can definitely replace this h with m sub h of n. Okay. So having said that, what we really need to understand now, the real challenge is to link this entire process to E out, because remember that was the whole point of doing this analysis, that E out reaches to E in plus the error bar, and we have a lot of information about the error bar now, given that we have the m sub h of n with us. So we want to link everything to E out. Like, how is it useful in sort of getting E in close to E out, right? That was the original thing. And then there is this rigorous proof that's given in the textbook for those who are interested. But from the perspective of the course itself, we are giving, like, I'm giving you this high level idea of how the proof works so that we can create a relationship here with E out. And that's what we're going to look at now. Okay. So let us consider that I'm taking out another sample from my from this universe of data, which is now known as D prime, right? And this is a fictitious data set. Maybe sometimes people call it ghost data set. You can think of it as a test data set, right? So again, this is another sample. And the way this is like different from E in, from the sample on which we calculated E in, is that this E in prime here will be calculated by generating not the same sample but another sample, and then the error is computed, right? This E in is computed on this new sample. So we will get a different E in prime. And remember, G wasn't selected on this new sample, right? G wasn't selected on that. G was selected based on E in. So E in prime is like a test error on n new points. Now, obviously, E in deviates from E out. We know that. Which implies that E in also deviates from E in prime. Why? Because E in prime is considered to be closer to E out. And this relationship is again via the Hofting's bound, right? Now this is compared to E in, it's considered closer to E out in and that's quite understandable, because now the G wasn't calculated on this sample, so this like actually comes out from that universe of data set in which we want to answer certain questions, right? So that's why this is considered closer to E out. Okay, so if you look at the PDF here on the left-hand side in this Gaussian PDF, essentially, what we get is that E in and E in prime obviously have the same distribution, of course, because we got the samples from this universe, which is the same for both of them, correct? But after multiple analysis of like different samples, what we arrive at is something which looks like this. So basically, this is telling us, of course, E in prime deviates from E out and E in also deviates from E out. But the fact that E in prime is closer to E out tells us that the probability of the deviation between these two quantities, the first sample and the second sample, right, is greater than, as you can see here, at least like half of the times, maybe another way of putting it is half of the times the deviation between E in and E prime is greater than the deviation between E in and E out, right? So this is an important result from the perspective of kind of creating a relationship between E in and E out, because we found another sample which is sort of representing E out, not quite, but it is there, right? And we also know that there is a deviation between this E in prime and E in, and that deviation, of course, is greater than at least half the probability of the deviation between E out and E in. Okay, so if we have this information with us, given like two samples, we can, like, this leads us to something that's really useful. But then we have to update whatever results we have, because like all our analysis will now be based on these two samples instead of one, right? And as I said, like I cannot have the entire universe, but I can definitely get this another sample on which G wasn't based on, right? And I also know that this was going to deviate from E in, and I also know that this is a representation of E out in the sense that it's closer to E out, right? So based on that, a few updates that I need to make on the analysis that we did until now is that all the dichotomies that we were trying to kind of list on endpoints will now be applicable to two endpoints, right? Basically, now we are interested in how many functions can be implemented for 2n, because now the sample is n and n for E in and E prime, E in of like the original sample and E in prime, right? So all of that is good. All we need to do is analyze the growth function for 2n points. The good thing is this does not affect, so this does not affect or impact the polynomial nature of the bound, right? So this does not affect the polynomial nature of the bound, which is good news for us. The only thing is that we, instead of n, I replaced it with 2n. 2 is a constant, so you understand that it doesn't impact a lot except for a certain technical details. And then what we'll see is we will be dealing with we will have a hypothesis set of size at most 2n. Okay, so all of this analysis, the relationship between E out and E in, and the update of my growth function and the definition of that leads us to something that's known as the famous bound, which is known as the VC bound or the Vapnik-Chervonenkis bound. And we are going to use this a lot throughout. Why? Because this is the bound that helps us link E out with E in, and all three equations here are valid. So you can tell that there are certain updates in what we know, right? So the probability of bad and the probability of good has been updated with certain constants because of the relationship, because of the analysis that happened here, right? So a few constants have been included in the equation, but that does not impact a lot here because all of those are constants. The rest of the analysis, the rest of the conclusions that we derived from our entire analysis hold here. So basically, mostly I'll be bothered about this equation here, which was the original Hovning's inequality. So we have, with high probability, this equation holds, right? And notice like with the numbers with the red here are kind of signifying that we have these constants updated, but the good thing is we have the m sub h of 2n included there, which is bounded by a polynomial. And as we said, the polynomial bound wasn't getting affected with these constants. So all of that is good, right? And what we have accomplished here is the first step of learning, wherein with some predefined probability, and like basically what we call it is like with high probability, I can say that this holds. Given some error tolerance and a sufficiently large data set, we can ensure that E out is indeed almost equals E in of G, of course, right? So that was our goal in throughout this entire lecture, and we are able to achieve this with this VC bound. And going forward, we are going to utilize this a lot, and we're going to build on that. But this equation is going to stay with us the way it is. So that's it for this lecture. most likely see you in the next lecture. That's going to be lecture 7.